Hello all, welcome to this course on time series modeling and forecasting in R. Now again, if you see in front of you, we have the R window open. So it means that in today's session, we'll talk briefly about some practical angles of, let's say, forecasting. Okay? So the entire today's session would be kind of focused on practical aspects of forecasting. Now again, if you remember very briefly, just to revise quickly, over the last 4 sessions in this week, we've talked briefly about different kinds of forecasting techniques. So of course, when the model is ready, so again by ready I mean that you fitted a particular model to the data set, then you've made sure that all the assumptions are being met or not, and then that exercise was called as diagnostic checking. And once you're through with all these processes or all these stages, then the ultimate stage is forecasting, where you sort of forecast down the line in the future depending on some historical information. And again, if you remember, some of the forecasting techniques we've covered in this week are some smoothing techniques. So let's say simple moving average smoothing or exponential moving average smoothing, right? And then we talked about double exponential or triple exponential, which had some other names also, such as let's say Holt's method or Holt and Winters approach, and so on and so forth, right? So particularly in today's session, we'll tie all these things down and then try to explain using a practical data set as to how one can forecast down the line if you have some available historical data with you, right? Now again, this would be the typical R window to start with, and then again we'll try to import some libraries again. So the first library we want is called as TTR. So as you see in front of you in line 1, and then the full form of TTR is interesting. So it's called as technical trading rules, right? So if you remember, if you want to forecast any stock price or something like that, then people often apply some technical indicators. So let's say moving average or RSI or MACD, right? So these are some well-known technical indicators. So this package sort of helps us to sort of draw some of the moving averages and then implement them on some real data sets and then eventually forecast, okay? All right, and then again, if you want to run a particular line on Windows, you can either click on this run that you see here, or you can actually click Control Enter, right? And similarly, if you have a Mac and if you're working on a Mac, then you can directly click Command Enter for running a particular line, all right? Okay, now initially in this video or in this session, we'll focus on 2 specific data sets, and probably we've covered these data sets in the earlier code sessions also. So the first one is called as NOTAM data set. So we'll fetch the data first. Let's say data and then NOTAM. So name of the data set is NOTAM, right? Now again, if somebody does not remember as to what this data set means, then I can quickly write down something like question mark and then NOTAM, right? So if you do something like question mark and then NOTAM and then hit enter, then it sort of gives you a small description of what exactly the data set is, right? So the NOTAM data set focuses on this thing. So average monthly temperatures at Nottingham. And then by the way, Nottingham is a county in the UK between all these years. So let's say 1920 to 1939, right? Now a couple of things to focus here. So you have a monthly temperature sort of a data, and then immediately if you have any monthly temperature data, then the immediate thing that should come in mind is there should be some seasonality present, right? Because we've discussed a number of times in the previous lectures also, if you're working with any temperature data per se, so temperature data or let's say rainfall data, humidity data, right? All these contain some seasonality aspects, all right? And then if you go down the line, then it sort of gives you a small description also. So a time series object containing the average air temperatures at this particular location, which is Nottingham, and particularly Nottingham Castle. So you have this Nottingham Castle in the county of Nottingham or the town of Nottingham in the UK, and then in degrees Fahrenheit over 20 years, so 1920 to 1939, right? And by the way, this is the source. So again, if somebody is more interested in sort of delving deep into a particular data set or a particular function in R, then R sort of nicely gives you the source of the data set also. So this data set was picked, or it was kind of discussed first in this book here by Anderson. So time series analysis and forecasting, the Box-Jenkins approach, all right? And then down the line, it sort of gives you some examples also. So let's say if you want to implement this data set using some basic techniques, right? So how can you do it, right? So getting the help command by using question mark sign, right? So a general syntax is question mark followed by any name of the data or the name of the function that you want some information on, right. And R sort of nicely combines several details about the particular data set or the function, from which you can get multiple further sort of ideas, okay. Alright, so coming back to this, so we will sort of work with this data. So we fetch this data notem, and then force notem. So force notem just ensures that you are kind of sticking that data inside the R environment, nothing more than that. So let's say force notem, right, and on top of that you can see that it sort of gives you the actual data also, right. So let me scroll up, and then again, since I told you that you have a monthly sort of a data, so January, February, March, April, all the way up to let's say December, and then over all the years. So the first column kind of gives you the years, and then all the subsequent columns gives you the months, right. And all these values that you see inside the table are nothing but the actual temperatures in Fahrenheit, okay. Alright, now the essence of kind of using this data, and then the first thing that we will do is sort of decompose, right. And then we have talked about time series decomposition sort of long back in one of the earlier sessions. So time series decomposition, if you remember, is nothing but to split the data set into its several parts. So let's say trend or seasonality or irregular fluctuations, etc. Okay. And in R you have this very easy command called as let's say STL, right. So STL sort of splits the data into different components. Okay. So it says here that decompose the time series into seasonal, trend and residual factors. Okay. So we will see what this command gives you, and then we have given it a name. So notem underscore STL. Okay. Now what we will do next is we will plot the actual data. So plot notem, right, and then here you see the actual plot of the data. So I'll sort of zoom this in a short while, right. And then the second plot we'll do is notem underscore STL, which is the decomposition plot, right. And this is a very typical decomposition plot. So what we'll do is we'll sort of zoom this plot, right, because the decomposition plot also gives you the underlying data. And then this is a very typical time series decomposition, right. And then probably we've definitely seen this sometime in the previous lectures also. So what it tells you is how the actual data sort of behaves in the first row, and in the second row it sort of gives you the seasonal aspects of the time series as to how the seasonality angle behaves or how the seasonality aspect behaves, right. And then by looking at the second row, one can immediately tell that there has to be some underlying significant seasonality, right, because you see some constant peaks and constant troughs there, right. Then third row tells you that if the data set contains any trend or not. So what do you think? So do you think that the data set contains any trend? Probably not, because otherwise you will see a clear trend here. So let's say upwards or downwards, right. But then since this is sort of in between some fixed horizontal bands, then one should not expect that there should be very high trend in the data or something like that, right. And then again the last row sort of tells you the remainder aspect. So once you remove the seasonality and the trend, whatever remains in the data is nothing but the remainder part. Okay. So my strong suggestion is that if you are trying to sort of analyze or even go ahead and then do forecasting using any practical data set, all these are sort of initial ingredients that one should focus on. So let's say time series decomposition, some initial plots of the data, so let's say a scatter plot, or so all these are kind of starting points if you want to analyze a practical data set, and then eventually the last step would be forecasting, of course, alright. Okay, so we'll close this now and then go back to the code. Now using the decompose series, we want to extract some time series. So let's say 1 to 12 and then the first column. So what do you get by doing this is nothing but you get the data set, right, of the, so this is sort of telling you some adjusted sort of a series, right, because here you see some negative values, right. So if you want some adjusted series, right, then you can sort of use such a command basically, okay. Alright, so now we'll shift to another data which is sort of air passengers, and then again I'm pretty sure that we've used this air passengers data quite often also in the previous code sessions or previous practical sessions, right. So we shall first fetch the data air passengers, and again the same thing. So again, if you don't remember what this data set is all about, then probably again you can look at the earlier videos, or the technique is you click question mark and then write down the name of the data set, which is air passengers. Now again, one thing here if you notice is that you need not even write down the full name of any function or any data set which has been called in the R environment. So since we've already called this data, so you can write down air and then basically click one of these. So I'll click the first one because we want some information on the actual air passengers data set, right? And then you sort of hit run, or and then again the same thing. So if you look at this window here, it tells you a small description about the air passengers data. Now again, I'm pretty sure that many of you might remember this data set. So we worked with this data set, and again the reason why I picked the same data set is just to sort of obtain some consistency over what we are doing in the practical sessions, right? So if you bring in some random data sets every time, then you might not be able to sort of connect the lines there, right? So since we worked with this air passengers data even before, let's say for model fitting or diagnostic checking, so why not just extend that and then try some forecasting techniques, okay? But again, just to quickly revise as to what this data set means, so this air passengers data sort of gives you the monthly airline passenger numbers between 1949 to 1960, okay? And again a very small description. So let's say the classic Box and Jenkins airline data, and again the same thing. So monthly totals of international airline passengers between 1949 and 1960, right? And then how would you use it? So usage, right? And then format. So format is, this is a monthly time series in thousands, okay? And lastly, this is the source. So Box and Jenkins and Renzel, and then this is again a book. So time series analysis, forecasting and control, right? And then some examples. So let's say immediately if you want to run some ideas on this data set using the air passengers data, then using some of these examples, you can actually, let's say, fit some plots, or fit some linear regressions probably, and then test some things out, and so on and so forth, okay? Okay, so again we've already fetched the data using data air passengers command. Now again what we'll do is we'll again decompose, right? So again, like I said, so time series decomposition has to be there if you're sort of analyzing any practical data set as a very initial step, okay? Okay, so and then here if you notice we will use this command instead, so decompose. So lastly for the NOTAM data set we use STL command, right? But then one can do it using either STL or decompose, okay? And here one can actually specify whether we want an additive decomposition or a multiplicative, right? So all these things we've kind of discussed in the theory session. So additive means that each component, trend, seasonality and irregular components are sort of added together. So T plus S plus I, right? As opposed to that, if you have a multiplicative sort of a type, then we sort of multiply each of the components. So trend into seasonality into I, okay? Alright, so we'll see how the decomposition looks like, right? And then now what we want to do is we want to extract the seasonal components out of that. So let's say if you want to extract the seasonality aspect of the data set, then this is exactly how the seasonal component would be fluctuating over all the months. So again the first column gives you the years, and then each subsequent column gives you the corresponding months, and then all these values sort of tell you the seasonality component for that particular year or that particular month, okay? Now here clearly you can see that the seasonality values don't change over the years, right? Because what's happening here is, let's say minus 24.74. So this value is the seasonal value, right, in the month of January, or let's say minus 36.18. So this is the seasonal aspect of the time series in the month of February, and so on, right? And obviously as you go down the line, so let's say July, August, so 63.83, 62.82. So all these are seasonality values extracted from the decomposition for that particular month, alright. So such things could be done once you sort of have a decomposition of a time series and so on and so forth. And now if you want to see that plot, right, if you want to obtain that decomposition plot, you again have to apply the STL technique. So STL underscore air is nothing but STL applied on air passengers, and then S dot window is periodic. So this is more like a syntax, okay? Alright, so we'll see how the decomposition looks like, right? And again, let's say if you want to extract some information of or from the decomposition that we have done, and then one can actually do it using this way, alright? Now again, if you want the plot, right, So if you want the plot of the decomposition, then I can actually scroll up and you can actually use plot and then the decomposition in terms of STL. So here, since we have given it a name of STL underscore air, so I can simply do something like, let's say, plot, and then inside round brackets I can write down STL and then underscore air, okay, because this was the name for the decomposition that we have done, right? And then if you run this, then you will see that you will get the decomposition plot here, okay. So let's zoom this and then see what's going on. So again, the same story. So the first row gives you the actual air passengers data and then how it behaves, and now the second row sort of tells you the seasonality aspect of that, and then clearly again you can see, or you can tell that there is some substantial significant seasonality which is present, right? And now surprisingly or interestingly, you also have a trend there, right? Because the third row sort of indicates very clearly that you have a very strong upward sloping trend. And then lastly, the remainder aspect. And here one more interesting aspect in the remainder part is that, can you see some periodicity in the remainder? Right. So the remainder itself is not completely random, right? And one more thing is that if you go down the line here, let's say 1958 or 1959 or 1960, then you can clearly see that the variance is also increasing, right? Because initially all the spikes are kind of very tight, but then as you go down the years, let's say towards the end of the time frame, you can actually see that all the spikes are kind of expanding and then the variance is actually increasing also. So air passengers data is a very famous data which people analyze, and why? Because this is a completely non-stationary data to start with, and this data sort of contains all the three aspects of non-stationarity. So trend, seasonality and changing variance, alright. So trend is there, seasonality is there, and then as well as changing variance problem is there, right. So how do you analyze such a data? So how do you model, then how do you apply some diagnostic checks, and then eventually how do you forecast is the kind of theme of many experimenters or many analysts, alright. Okay, so we'll close this data set and then go back to the code. Now here what we'll do is we'll try some smoothing techniques. So eventually our goal is to do some forecasting or apply some forecasting techniques, right. So why not just start with some basic smoothing techniques. So for that what we'll do is we'll have a simple plot of the data set. So this is exactly how the air passengers data looks like, okay. And we've seen that in the previous decomposition plot also, okay. Alright, now this command that you see in line 29 just tells you or just ensures that you're kind of considering this air passengers term or the air passengers data as a time series object, okay. So we added this TS in front of that. So TS applied on air passengers tells you that you have to actually consider this as a time series object, okay, nothing more. And now here what we are doing is we are fitting a simple moving average smoothing technique. So can you see that? So SMA stands for simple moving average. And what is the order of that? So again, if you go back, let's say a couple of sessions in this week, right, then you should always remember that any SMA or any exponential moving average has some order, right, and then we've discussed that also. So so idea is to play around with the order. So can you sort of change the order, and then the idea is that if you change the order, then which order sort of gives you the best fit, okay. This should be the ultimate goal, isn't it? So I can play around with the order. So let's say I can take 3 or 4 or 5 or let's say 7, 8 and so on, and I can see that how the SMA is sort of fitting the actual model, or how the smoothing technique is sort of getting placed on the actual data set, and then from all the visual plots and visual checks I can pick the order where I think that the fit is sort of the better or the best, okay. So here initially what we are trying to do is we are fixing the order to be 3, right. So again, air passengers underscore TS underscore a simple moving average smoothing technique where the order is 3, right. And then now we'll see that what happens. So if you run this, then this is now stored in this name, right. And now what we'll do is we'll see the actual data. So this is the actual data, okay. So this is the actual data, right. And then the next thing what we'll do is that we'll actually see the SMA values. So since we fitted this SMA3 model, right. So now we'll see that what values the moving average or the smoothing technique with an order of 3 is giving us, right. So I think this is just for comparison. So we can place these two data sets side by side and then probably gauge on the fact that are they giving us a superior model fit sort of, or is this SMA 3 indeed a better fit, right? And how could you do it? I mean, you can compare, let's say, piecewise. So let's say the first value is 112, then 118, 132, 129. Now remember one thing, since you're applying a simple moving average of order 3, now again if you go down, so these are the moving average values. You will see NA for the first and the second one. And why is that? Because there won't be any values for the first and the second one, since you're using a window size of 3, right? Because the idea behind SMA is that you go back in the history and then you're taking the average of the last 3 values, right? So since you're using SMA 3, then there has to be no value here in the first one as well as no value in the second position. Now the third value is 120.66, then the fourth value is 126.33. Now you have to actually find out, are they matching with the actual observation. So here the third value is 132, then the next value is 129, right? So this is just a rough idea as to how can you compare by keeping these two subsets of the data side by side. So the actual data and the SMA 3 values, right? But one can actually plot the SMA 3 fit also, right? So this is nothing but the simple moving average smoothing technique and then the plot of that you see here, alright. And the command that you see in line 34 is essentially what would happen if you subtract the two. So rather than comparing one data point with the other from the two subsets, why can't we simply subtract and then see that if the subtractions or the resultant subset is close to 0 or not, right? So if all the values are sort of close to 0, then we'll say that piecewise they should be matching, alright. Okay, and then here what we're doing is we're subtracting the actual data and the SMA 3 values and then plotting that. So this is that plot. Let me zoom this, right? And then we sort of discuss that what is happening here. So firstly, if you see that pretty much the values are kind of revolving around the line 0, which is exactly what we want, right? Because if you take the actual data and subtract the fitted data, so something like y minus y hat, similar to what we do in regression also, right? So these are nothing but the residuals in some sense, right? So the residual should revolve around 0 because all the errors should be really close to 0. But there might be some problem here because you see some periodicity. So you have like peaks and troughs which are kind of repetitive, and then down the line you can clearly see that there is a changing variance problem also. So as you go down the line, then the variance aspect in the underlying data set or the underlying residuals is sort of also increasing, right? So these are some observations that the experimenter can make by simply plotting the residuals or nothing but y minus the y hat values, okay. Alright, now what? So now as a comparison, what we do is we'll plot or we'll kind of find out another SMA with an order of 8, right? And such things can be done very easily by changing this n to be whatever number you want. So this n is the order of the SMA. So earlier if you go back, then here the n was 3, but then here if you see that I'm changing the order from 3 to 8. Now how the performance will be, so we'll find out. So let's say we've found out the SMA 8 values. This is the actual data. This is the SMA 8 data, right? And now this is exactly how the SMA 8 plot looks like, and this is exactly how the plot of the residuals look like. So again let me zoom this one, right? And then if you zoom it further, then this is exactly the behavior of the residuals of a SMA 8 fit, right? And then one again problem here, I'll say that if you sort of compare this plot with the earlier residual plot where we used SMA 3, one can clearly see that the amount of changing variance is predominantly high in this fit because all the peaks if you see are really higher than the earlier plot, right? This could be a problem, right? Because we want the variance to be as less fluctuating as possible, right? So if the variance is fluctuating that much in SMA 8 as compared to SMA 3, then probably one should actually go with SMA 3 instead. Alright. So these are just again some observations that one can actually make from creating such plots. Alright. So this was SMA, right? SMA, and then now EMA, right? So EMA is what? So EMA is exponential moving average smoothing. Alright. So again the same thing. So we'll try to fit two EMAs. So the first one would be of order 3, right? And then second one would be of order 8. So let me run both of them simultaneously. So the first one has an order of 3, and then second one which is given by this name. So EMA 8 underscore air passengers is with an order of 8. Now again the same thing. So we'll create 3 plots. So the first one is the EMA 3 plot, right? This is exactly how the EMA 3 smoothing fit looks like. Then the second one would be EMA 8, right? So this is exactly how the EMA 8 smoothing fit looks like, right? And then the third one is of an order of 12 now, right? So if you see here n equals 12. So how would that plot look like? So this would be that plot, right? Now one feature or one observation which one can find out using all the 3 plots is that the EMA 3 plot and then EMA 8 plot and then EMA 12 plot. So if you go on increasing the order, can you see that you're kind of getting smoother and smoother plots towards the end? So this is EMA 12. Let me show you EMA 8. EMA 8 is this, and then EMA 3 is something like that, right? So can you see that EMA 3 would be kind of more suitable for the underlying data set as compared to, let's say, something like EMA 8 or EMA 12, which are much more smoother, right? The idea is that we want to preserve the underlying tendencies of the data set also, right? So if you have a really smooth kind of a EMA or SMA whatever plot, then that might not serve the purpose. Okay, so now we're almost there. So now the next thing we'll do is we'll try to apply the Holt's technique. Alright, so Holt's exponential smoothing, which is also called as double exponential smoothing. Now again, if you remember, we discussed in the last lecture also that if you want to implement this in R, you have this common command called as Holt-Winters. So inside this Holt-Winters itself, you can actually specify whether you want a Holt's technique or a Holt-Winters approach. Okay. Alright, so we'll run the Holt-Winters command, and here how do you specify that you want a Holt's technique and then not a Holt-Winters? By using this syntax. So gamma equal to false. If you specify gamma equal to true, then it also estimates the gamma parameter, and then the gamma parameter is associated with Holt-Winters and not the Holt's. Okay. So if you specify gamma to be false, this is actually Holt's technique. Alright. Now again the same thing. So this is the value. So by the way, this is what the syntax of the output of the Holt's technique tells you. So it sort of gives you the optimum alpha value, which is 1, optimum beta value, which is 0.0032, and then the underlying coefficients, right, of the Holt's technique. Alright. And then now can you extract the SSE value of this fit? So SSE value happens to be that one. So 163,634.1, right? And then eventually can you forecast it or can you plot it? So this is nothing but the Holt-Winters filtering, and then this is, by the way, simply Holt's and then not Holt-Winters. And then you can see that I'm kind of getting a very superior kind of a model fit here. Right? And now if you want to forecast in the future, right? So so for that you require this library which is called as forecast. Okay. And then what we'll do is we'll sort of forecast the air passengers data in the future. So we'll use this command called as forecast, right? And then we'll sort of give you a plot of the forecast also. So can you see here? So this is the actual data, and this is exactly how the forecasts are looking like. And now you might wonder that forecast using which technique. So again, if you come back to the code, so since we specified air passengers F, so air passengers F is, again if you scroll back slightly, this is given by the Holt's technique, because this is the name we gave for the Holt's technique, right? Air passengers F. So whatever fit you specify here, in this case is the Holt's technique, then the forecast would be sort of from that or using that technique. And here you can clearly see that the forecasts are sort of not matching the actual data set, right? I mean they're not able to preserve the seasonality. Can you see that? Because the forecast is almost a horizontal line, right, which is not preserving the seasonality aspect. So can you do better? The answer is yes. So now the last thing is we'll try to implement the Holt-Winters approach, because remember one thing, that if the underlying data set contains seasonality, there is no point in applying Holt's technique. One should actually go with Holt-Winters. Alright. So we'll do the exact same thing, but then small tweak here is that we are applying Holt-Winters on the log of the data. And why? Because again if you remember, there was this changing variance problem. Now how do you correct the changing variance problem? Is by applying some transformation. So let's say log or square root, etc. Right? So we'll apply this Holt-Winters technique on the transformed data set, which is log. Alright. Okay. So this is the forecasting, or this is the model fit, right? and then this is the SSE value 0.2030, and this is the Holt Winters filtering. Again, you can see that it sort of preserves the seasonality and the trend, etc. And the last thing is forecasting. So, forecasting using which method now? So, forecasting using the Holt Winters approach, alright. And here you can clearly see that if you are actually applying a Holt Winters approach rather than a Holt's technique, you are actually preserving both the trend and the seasonality, etc. Right. So, the summary here is that if you have both trend and seasonality, one should actually go with Holt Winters approach so as to preserve the trend aspect and the seasonality aspect, rather than something like, let us say, SMA or EMA or a Holt's technique. All right. Thank you.